Welcome to Edupedia Word Videos. In this video, we will be discussing decimal expansions of rational numbers. Friends, decimal expansions can be broadly divided into three categories. The first is terminating decimal expansion. For example, if we have a number 65 divided by 2, then on performing the division process, we can say that its decimal expansion is 32.5, and at this stage the division process is terminating, and hence only one digit in the decimal part, that is 5. After that, the decimal expansion terminates. Similarly, we can have other examples like 0.3, 0.36, 21.9, etc. Such kind of decimal expansions that terminate after some digits are known as terminating decimal expansions. The other category is non-terminating and repeating decimal expansion. For example, we have a number 210 by 11, then on performing the division, we can say that this 1 is coming again and again in the decimal or in the division process, and hence this 09 is coming again and again in the decimal expansion of this number. Therefore, the decimal expansion is 19.09, 09, 0909 and so on. Such a decimal expansion is non-terminating because of this continual process, and the division process will never end, and repeating because this 09 is repeating again and again. Now the third category of decimal expansion is non-terminating and non-repeating. For example, we have a number under root 2. Its decimal expansion is 1.414, 213, 562 and so on. Clearly again it is non-terminating but also non-repeating the decimal part, because we cannot figure out any specific pattern which is repeating in the decimal expansion. Friends, these decimal expansions, the types, are also related to whether the number represented by them in fractions or this number is a rational or irrational. The first two categories are of rational numbers, whereas the third category, that is non-terminating and non-repeating decimal expansion, is of irrational number. Now we have certain theorems which will tell us whether the decimal expansion is terminating or non-terminating and repeating for a rational number. The basic of all the three theorems is same. The first theorem says, let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q. where P and Q are coprimes, and the factorization of Q is of the form 2 raised to power n, 5 raised to power m, where n and m are non-negative integers. So we have a rational number whose decimal expansion is terminating. So let us have a terminating decimal expansion, say 32.5, that we have earlier used in the example. So theorem says, since it is a terminating decimal expansion, therefore x can be expressed in the form of p by q, where p and q are coprimes, and q is of the form 2 raised to power n into 5 raised to power m. Clearly, one way to represent 32.5 is by removing this decimal and putting the required amount of tens in the denominator. But we can see that 3 to 5 will have a factor 5 and 10 will also have a factor 5, because 3 to 5 can be expressed as 65 into 5, whereas 10 can be expressed as 5 into 2. So when we cancel this 5 with this 3 to 5, we will get 65. So we will now have 65 by 2. Now we can say that these two are coprimes, because 2 cannot be a factor of 65 and 2 cannot have any other factor in its prime factorization. So clearly in the p by q terms, now these are coprimes. The theorem says that it can be expressed in the form p by q, where p and q are coprimes, and factorization of q is of the form 2 raised to power n into 5 raised to power m. Now this q, that is 2, can be expressed as 2 raised to power 1 into 5 raised to power 0, because 1 is anything raised to power 0, that is 2 raised to power 0 or 5 raised to power 0 or 7 raised to power 0 and so on. And 1 and 0 are non-negative, so this q can be expressed in this form also. Thus this theorem is explained with the help of this example. Let us have one more example, say 0.625. Again, the simpler way to represent it in fractional form is by removing this decimal and putting 3 zeros with 1, that is 3 tens, their products. Now 625 is nothing but 25 square, whereas this 1000 is nothing but 10 into 10 into 10, and 25 is 5 square. So we have 5 into 5 whole square, that is again 5 into 5 over 10. 10 is 5 into 2, so we have 2 into 5 into 2 into 5 into 2 into 5. 3 5s will get cancelled and we are left with 5 over 8. Clearly 5 and 8 are coprimes, and the value q, that is denominator 8, can be expressed as 2 cube from here also, which can further be expressed as 2 raised to power 3 into 5 raised to power 0. So clearly it was also a case of terminating decimal expansion, and we can see that it can also be expressed as p by q form, where q is of the form 2 raised to power n, 5 raised to power m, where n and m are non-negative integers. We can have some more examples like 0.13, which is 13 over 100, or simply 13 over 10 into 10, that is 13 over 2 raised to power 2 into 5 raised to power 2. Clearly 13 and 100 are coprimes, so 13 over 100 or 13 over 2 raised to power 2 into 5 raised to power 2, that is 100, can be expressed in this form 2 raised to power n, 5 raised to power m, where n and m, that is 2 and 2, are non-negative integers. One more example, that is 0.208. It can be first simplified as 208 over 1000. Now 208, it is 2 into 104, and this 104 is 2 into 52, 52 is 2 into 26, whereas 26 is 2 into 13. So we have 208 as 2 into 2 into 2 into 2 into 13 over 1000, which is 2 into 2 into 2 into 5 into 5 into 5. This will amount for 10, this will again amount for 10, and this will again amount for 10. So 10 into 10 into 10 is 1000. These 3 2 will get cancelled, and we have 2 into 13 over 5 into 5 into 5. Clearly the prime factorization in denominator and numerator have nothing as the common factors, so they are co-primes, that is relatively primes. Thus this 0.208 is again expressed as 26 over 5 cube, or simply 26 over 125, that is p by q, where p and q are co-primes. And again this q is expressed as 2 raised to power 0, 5 raised to power 3, that is in the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. So we have seen that if the decimal expansion is terminating, we can express the decimal expansion as p by q form, where p and q are co-primes, and q is of the form 2 raised to power n into 5 raised to power m. Friends, the second theorem says, let x equal to p by q be a rational number such that prime factorization of q is of the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. Then x has a decimal expansion which terminates. So it is a theorem which implies the same significance as the first theorem. So let us understand this theorem. Let us have first a rational number, say x equal to 7 by 8. Now we can view this number as 7 by 2 cube. Further, we can also modify this number by multiplying and dividing it with 5 cube. Thus we will get 7 into 5 cube over 10 cube. Multiplying the denominator by 5 cube has also resulted in calculating the decimal part of this number with a greater ease, because this will give us 125 into 7, that is 875 over 1000, which is nothing but 0.875. So clearly this rational number has the prime factorization of this form for q, that is denominator 2 cube, or we have multiplied and divided by 5 cube, and we have get 2 cube into 5 cube. So if the denominator has the prime factorization of this form, then we can say that its decimal expansion will terminate. Clearly it is a terminating decimal expansion. We can have one more example, say 11 over 25. Now 25 is nothing but 5 square. Let us check if its decimal expansion is terminating or not. Firstly, 5 square can also be viewed as 2 raised to power 0 into 5 square, and we have no other prime factor in the factorization of denominator like 3 3, 7 and so on. Now if we perform the decimal expansion by multiplying and dividing by 2 square, we will get 44 over 100. Clearly we can easily write the decimal expansion as 0.44, which is terminating. So we can look at the denominator and see if it has the decimal or the prime factorization of the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. Then we can say that its decimal expansion will be terminating. Now the third theorem is just the opposite of this theorem. The third theorem says, let x is equal to p by q be a rational number such that the prime factorization of q is not of the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. Then x has a decimal expansion which is non-terminating and repeating or recurring. That is, if the denominator has the prime factorization not of the form this, that is 2 raised to power n into 5 raised to power m, where n and m are non-negative integers, then the decimal expansion will be non-terminating and repeating. Let us understand this theorem. Let us have an example, say 4 by 13. So here p is 4 and q is 13. Clearly 13 is equal to 13 into 1, that is, the prime factorization don't involve 2 and 5 only. 13 is another prime factor involved in the prime factorization of 13. So this decimal expansion according to the theorem will have non-terminating and repeating type. In fact, if we perform the decimal expansion of this number, we will get we can see that now the stage is repeating. That is, after this stage again this process will repeat, and hence the decimal expansion will also repeat, and the division process will never terminate. So clearly it is a non-terminating and repeating decimal expansion. Why? Because the prime factorization was not of the form 2 raised to power n into 5 raised to power m. There is also a prime factor 13 involved in the denominator. Now let us have one more example. Say 19 over 117. Again its prime factorization is having some prime factor other than 2 and 5, so it will be a non-terminating and repeating decimal expansion. And if we perform the decimal expansion of this number, this rational number, we will get 0.162393.162. that is, this 162 will, this stage will again start repeating. Why? Because Q, that is 117, is not or cannot be expressed in the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. So friends, like the number 19 over 117. So the prime factorization of 117 is, see, 117 is 13 into 9. So its prime factorization will be 3 into 3 into 13. And 19 is a prime. So we can say that 19 and 117 are co-primes. That is, they are having no common factor in their prime factorization. Thus, we have represented the denominator in the prime factorization form, and we can see that it is not of the form 2 raised to power n into 5 raised to power m, because there are some other primes like 3 and 13 involved in the prime factorization. Thus, by the theorem that we have discussed, we can conclude that it has a non-terminating and repeating decimal expansion. In fact, if we divide the number 19 by 117, we will get the decimal expansion as 0.162.393.162 and so on. So this block will get repeated over and over again. So friends, we have studied that the rational numbers can have the decimal expansion as either terminating or non-terminating, but repeating. For the case of terminating decimal expansion, if x is a rational number in p by q form, then q must have prime factorization in the form 2 raised to power n into 5 raised to power m, where n and m are non-negative integers. Whereas in the second case, where non-terminating but repeating decimal expansion of the rational number, q's prime factorization is not of the form 2 raised to power n into 5 raised to power m. So let us quickly revise with some examples what we have learned so far. Say if we have a number 13 over 3125. Clearly 13 is a prime and 3125 can be expressed as 5 into 6 to 5, thus 5 into 25 square, that is 13 over 5 raised to power 5. Now clearly the prime factorization of this lower number involves only 5, and in numerator we don't have any 5, so they don't have, the numerator and denominator, they don't have the common factors, and hence they are co-primes. Moreover, the denominator can be expressed in the form 2 raised to power n into 5 raised to power m only, without any other prime factor. that is 2 raised to power 0 into 5 raised to power 5. Thus we can say that the decimal expansion of this number is terminating. Now we can have one more example as 77 over 210. So the prime factorization is 7 into 11 over 21 into 10, that is 7 into 3 into 10 in 5 into 2. So if we remove the 7, that is the common factors, and convert this thing into the prime factorization or the co-primes, we have 2 and 5 in the denominator as well as a value 3. So apart from 2 raised to power n, 5 raised to power m, we are having other prime as 3. So we can say that it will be of the second type, that is non-terminating and repeating decimal expansion. So friends, this was all on the topic decimal expansions of rational numbers. Thanks friends for visiting Edupedia Word videos.